Hello and welcome to a new video. This is for Precalculus using the Math UC curriculum, and today we are in Lesson 10, verifying trig expressions and identities. And one of the things to point out here is this lesson definitely takes things from the majority of the lessons before this point and has us kind of putting them together. That being said, I don't think it's harder than what we did last lesson. I think lesson 9 with all the proving of those trig identities, I think that's definitely like kind of a peak of hardness, at least for now, on what we've got going on. But we are still going to be using like some of those things, and I think that we'll continue proving things in the homework probably forever. I don't know. I haven't looked that far ahead. So keep that in mind, that that you'll have lots of opportunities to practice proving things, and hopefully that's great. So let's look at this. If you want to download this notes page to use to follow along, you can click the link in the description, and let's go ahead and get started. Also, besides having a notes page to use to write this down, it would also be helpful for you to have some sort of like identity sheet that you're using, unless you feel like you already have them memorized. Also helpful is a unit circle to have as a reference. You don't technically need either of those things, but they can help. And the idea would be that maybe if you're relying on those things a ton at the beginning, hopefully the more problems you do, especially the unit circle part of it, the ideal situation would be that as you do more and more, you have to rely on those tools less and less. If you're headed towards like a college level calculus class or AP calculus, you're definitely going to need to memorize these things. But if you're not, then it's whatever. All right, so this says evaluate the expression using ratios, I added, or the unit circle, and leave the answer in exact form, i.e. a whole number, fraction, or radical. It'd be easier in some ways to say, don't put it as a decimal. That's not exact form. Technically, if you put like 0.5 instead of 1/2, that's still exact. But again, like, why wouldn't you just put 1/2? We want to leave it as fractions, radicals, whole numbers, all that jazz. I don't know why you would change a whole number anyway. So we are going to look at this and say, okay, what is it that they want us to do? We have 3 cosine 60, and then we have 7 sine 30. And we are looking at this as they want me to find cosine of 60 and put it right here. So we'll have 3 times that amount. And they want me to find sine of 30, put it right here, and then we'll have 7 times that amount. We'll take those two products and add them together and see what we get. There's at least 2 ways to figure out cosine 60 and sine 30. One of them is just to draw yourself a special right triangle. Beautifully, beautifully done here. So this would be 30 and 60. The hypotenuse is 2. The shorter leg is 1. This is square root of 3, and then use the ratios for cosine and sine. The other way would be to picture in our head or use a unit circle and look at the points for 30 and 60. Whoops. Remembering that cosine is your x value and sine is your y value when you're using the unit circle. So this would be square root of 3 over 2 comma 1/2. And this would be 1/2 comma square root of 3 over 2. And I didn't draw the middle line because I'm being lazy. So when I do cosine of 60, that should be, I should look at 60, which is up here. I should do adjacent over hypotenuse, so 1 over 2. So cosine of 60 is 1/2. Now I'm going to do sine of 30. Sine of 30 is this one over here. That's opposite over hypotenuse. Just bit my tongue. Opposite over hypotenuse, which is 1/2. And remember, you might have actually realized those were going to be the same if you remembered way back whenever we like noticed that connection between cosine and sine of angles that add up to 90. But anyway, so we're going to do 3 times 1/2, which is 3 halves, 7 times 1/2, which is 7 halves. Add it together, we get 10 halves, which is 5. I think that some of our answers are actually going to end up nice like this, obviously. A lot of them are not going to end up really nice like this, but some of them have a chance to. Definitely this is one of those times where checking our answers, I mean, there's like never a good time to not check your answers, but checking your answers to see if you get 5, if it's really 5, super good idea. We've got another one with the same instructions here, example 2. But our trig ratios are maybe a little bit harder, maybe not. Tangent of 45 degrees, we need to visualize in our head or have in front of us some way of relating 45 degrees in tangent. Tangent is opposite over adjacent, or if you're looking at a unit circle, is y over x. And just kind of depending on how you do it, if you are using the unit circle and you're using y over x, you're going to end up with square root of 2 over 2 over square root of 2 over 2, which since those are the exact same, that equals 1. Same thing with a 45, 45, 90 with 1, 1, and square root of 2. This is opposite over adjacent. 1 over 1 is 1. So tangent of 45 is just 1. Now cosecant is the flip of sine, which means that it's hypotenuse over opposite. So we need to be thinking about our 30-degree angle or about our unit circle. Let's see. Hypotenuse over opposite, so 2 over 1, which is 2. I didn't actually mean to make these be so nice, so that's kind of awkward actually, because this is 1 minus 4, which is negative 3. Like, there's a super good chance that some of our answers are going to have like square root of 3 plus 5 or something like that. So hopefully that happens to us at some point. Like, if we had gotten 1 minus square root of 3, like, you'd just leave your answer like that, just kind of by the way. If you can't get rid of the square root in some way, like, which most of the time you won't be able to, the only way we can get rid of a square root is if there's a squared, and there wasn't a squared on this problem. So you may end up having to just leave it alone, just leave it as what it is, because we can't actually do 1 minus square root of 3 unless we're willing to get a decimal, which according to the directions, we are not willing. All right, example 3. Verify that these equalities are accurate by using the appropriate reference angle and proper sign according to the quadrant. Okay, so if we're looking closely at this, this is the main Pythagorean identity, the one that started it all. Cosine squared plus sine squared equals 1. But we've got 135 in for theta. And one of the things to note here is that whenever we look at those identities, and if we are filling them in with an angle, if our identity has theta in more than one spot, we have to put the same thing for theta in all of those spots. We can't put 135 for theta in one spot and then 225 for theta in another spot. So one of the other tricky things about this is that 135 is not in the first quadrant. So one of these two values is probably negative. And so when we're thinking about 135, we'd think that's 45 degrees past 90. So that's right here. So either looking at our unit circle at this point or making a reference triangle, we would get negative square root of 2 over 2, comma, positive square root of 2 over 2. So for cosine, which is our x value on the unit circle, or if you're looking at adjacent over hypotenuse, you should have negative square root of 2 over 2. Now, we're squaring cosine, so we're going to put that negative square root of 2 over 2 in parentheses and then put a squared on the outside. Same for sine. It's positive square root of 2 over 2. So we're going to put that in parentheses and square it. So the bright side on these is you don't have to check your answer because you already know this is supposed to equal 1, right? So you could check your answers and checking to make sure you did your math a correct way. But if you were worried how this was going to end up equaling 1, check it out. We square root of 2 and get 2, square the 2 on bottom and get 4. Both of these end up being positive because we square that negative away. 2 over 4 plus 2 over 4 is 4 over 4, which does in fact equal 1. This is a little bit more similar to our proving situation. It says verify, which is kind of the same word as prove, or at least similar. So it is the work that you're showing. Like, you have to show enough work to be like, oh yeah, you really did verify that. You didn't just say it equals 1. All right, example 4. So this isn't an identity that's on our sheet. And I guess actually the instructions don't even call these identities, they just say equalities. but you want to make sure basically that the left side and the right side actually equal each other. So we have the angle 240. We're being asked to find tangent, secant, cosine, and sine. So we better go ahead and figure out what is going on at 240. So either looking at your unit circle or just drawing the angle. It's down here in the third quadrant. It is a 60-degree reference angle if you're doing it that way. Or if you're using the unit circle, this point would be -1/2 comma square root of 3 over 2. And if you're like, well, why do you keep talking about both ways? It's because, like, I see the value of both ways. Like, I preferred to not have the unit circle memorized until all of a sudden I kind of had it memorized. And I also didn't know about the unit circle whenever I was taking precalculus and trigonometry originally, so you don't have to use it. The reference angle is easier for things like finding tangent of this. This is opposite over adjacent, or you'd have to put, this should be negative square root of 3 over 2. You'd have to put these over each other if you're using the unit circle, which the bright side here is the 2's cancel, the negatives cancel, and that gives us square root of 3 over 1, which is just square root of 3. So we've got square root of 3 plus 1 on top. So I'm glad this happened to us because I want to point out you can't add those together. You leave them separate. So this was tangent. Secant is the flip of cosine. So cosine is -1/2, so the flip of cosine is -2. So this is what we're hoping to get from cosine 240 plus sine 240. Wow, hoping to get this is kind of a stretch there. So 240 cosine, so adjacent over hypotenuse, or the x value, so that's -1/2. Sine 240 is opposite over hypotenuse, or the unit circle, negative square root of 3 over 2. So there's a common denominator. You might look at this and say, are those equal? Or you might be looking at this going, of course they're equal. I'd get a common denominator. I'd probably actually go ahead and rearrange the top here to make them look nicer. And then the difference between these is where the negative is. And you might be thinking, oh, these aren't equal because the right side has 2 negatives, the left side has 1 negative. But the way it works with fractions is to get this negative on the top right, to get these negatives out, we would factor them out, like so. And then that is what would allow us to move the negative to the bottom. Or if we move this on the left, if we move the negative up to the top, we have to distribute it to both things. Whichever way you want to think about it is fine, but that's kind of the process we have to go through. I want to be lazy and not rewrite this, but that's not me being a very good example. So I'd basically be moving this -1 down to the bottom, timesing it by 2. So ta-da! Don't really need to box out. That's not like my answer. It's just, I'm done. I'm excited. One more. This is not necessarily actually new to this section. I don't think it uses actually anything specifically related to this section, but I noticed that there was a question like this on the workbook, and I was like, you know what? That seems like something that might stump people, so why don't we go ahead and go over it? It says find the sine, cosine, and tangent for cosine theta equals 2.25 and sketch the triangle. Then find the angles of the triangle. Basically, it wants us to sketch a right triangle, right? Because we're using trig functions. And it wants us to use the idea that cosecant of theta is 2.25 and then use that to find sine, cosine, tangent of that angle, and then to also find the angles that we don't already know of the triangle. In the workbook, this is like 2 separate questions. It asks you the first sentence, and then on the next problem it says find the angles for the problem you just did. So let's start off by breaking down cosecant theta equals 2.25. Now cosecant is the opposite, or is the flip of sine. It would really be helpful if 2.25 was a fraction instead of a decimal. Your calculator actually would do that for you. If you type 2.25 and you have a TI calculator, you would press math, and then I think it might be the second choice that has like an arrow answer to decimal thing going on, but it'll, oh wait, no, we don't want it to go to decimal, we want it to go to fraction. It's the first thing. So you press math, enter, and it will change it to, this would be 9/4. Right? 9/4, because 4 goes into 9 twice with 1 left over. So 2 1/4. Okay. So I guess the other way would have been to think about this is we could have changed it to a mixed number first and then changed it to an improper fraction. But that's helpful because then we can say, well, sine theta is 4/9. So pick one of these angles to be theta, and then we can label the opposite side as 4. The hypotenuse is 9. We are going to, that was one of the things we needed to find, we are going to need to use the Pythagorean theorem to find the third side. So 9 squared minus 4 squared, which is 81 minus 16, which is something that ends in 5. 65. 65 is 5 times 13, so that does not simplify. So we've got sine. Cosine would be square root of 65 over 9 because it's adjacent over hypotenuse. Tangent would be opposite over adjacent, which is 4 over square root of 65, but we will rationalize that, which gives us 4 square roots of 65 over 65. And then we need to find these two angles. So the way to do that is to use an inverse trig function. So theta, and maybe we could label this other one x. And we actually need to use a trig function for one of them, and it doesn't matter which one we use. So if I like the fact that sine is 4/9, it doesn't have a square root, I could do inverse sine of 4/9, and that will tell me what theta is. When we do inverse trig functions, they're going to give us like decimals and things, so keep that in mind. Make sure you're in degree mode because that also matters. And around this to 2 decimal places, so it'd be 26.39. For our first angle, and then our second angle we'd do 90 minus that and get angle number 2 for our triangle, which would be 63.61. And voila, there we go. Thanks so much for watching. I think that this lesson should seem like easier than the last one, because it's not like at no point did we even have to really identify any of these identities, right? So it doesn't even matter if you believe they're true. They're telling you it's true. You're just having to show that like you can figure out what sine, cosine, and tangent of a bunch of different angles are. And so once you get the hang of that, then they should be easy peasy lemon squeezy. Thanks so much for watching. If you're not subscribed, hit that subscribe button and go ahead and hit the thumbs up while you're at it. I'd appreciate it. Thanks so much. Bye.